Okay, so our first speaker today is Brian Chung. He's a recent graduate of Boston College, and this summer he was working with Corné Kremmer at the University of Nevada, Reno as his science mentor, and Kelsey from the University of Colorado Boulder as his writing mentor. Brian, you probably saw, is our star on the advertisement for the Colloquium because he's a second-year intern, and so he's returned this year to do research. And we're going to hear about his work, a non-parametric approach to infer slopes from short time series with seasonal fluctuation, application to GPS time series.
Thank you, Aisha. As she said, my name is Brian Chung. I'm from Long Island, New York, and I'm happy to have just graduated from Boston College with a bachelor's in mathematics. So today we will be exploring how to approach short time series. There are two types of GPS time series that exist. There are long enough ones that you can infer slopes from, and there are short ones where you cannot use those certain types of estimators in getting a reasonable slope. So GPS stations track position data to the order of fractions of millimeters, and this is some of the types of instrumentation you might see. On the left, you have an antenna and a monument, which, as you will see, exist in thousands of places throughout the world. And on the right, you have a solar panel that charges a battery source, and also in there is a receiver, which is a hard drive where the data is stored. And the dimensions in which this data is stored comes in three. It's horizontal, so north-south, and east-west. And also the third dimension is towards and from the sky, the vertical dimension. This is the global distribution of GPS stations. As you can see, it's very far-reaching. These red stations are the magnet network through UNR, and those are some of the stations I visited this summer while doing field work. We were on the Colorado Plateau around this area. And those are some of the stations that inspired me because some of them produce short time series, and we're about to see how those occur. So short time series can occur as a result of malfunctioning instrumentation, natural factors, and anthropogenic factors. Certain stations like this, which is a PBO station, thank you UNAVCO, are very expensive, and they're super accurate and do really well with data and are very continuous. They have very reliable power sources, and they're constructed with very heavy instrumentation. So those are the well-behaved ones. But in the field, we were dealing with UNR's GPS network, and they consist of temporary sites, which you can even break down by hand. So this is me constructing one. And that's the solar panel and battery source for this GPS station. And those types of temporary stations are subject to certain factors that these stations are not. They're much more susceptible to the factors. So meteorologically, in the winter you get snow, and this is the before picture, and this is the after picture. So the snow can easily cover the solar panel, cutting off the power source to the battery. So this station would have stopped producing data once the battery ran out because there was nothing to charge it. Wildlife. This antenna is on the Navajo Reservation. We're fortunate enough to visit it. And here an issue was overgrowth. The overgrowth and bushes and trees were covering the solar panel, so it was affecting the power source. This was also a cattle drive we encountered right on the road, and it's not uncommon to stumble upon one of these stations that has been subject to livestock. And there are also wild horses in the area. Couldn't get a good picture of one, though. And by far the most common thing that I saw that interfered with the power source were mice. They were chewing on the wires, and sometimes they would go all the way through. And, you know, the nooks and crannies of GPS stations are very inhabitable. And anthropogenic factors, I was very shocked by this one. There's a number of stations that are subject to vandalism. It looks like a baseball bat was taken to this solar panel. Not the best picture of it, but the wires were ripped out and cut, and it was actually pretty disturbing to see. And this is a station that I did not get to see, but it was in the lab, and it was used for target practice with a shotgun. So those are also some of the ways GPS time series will stop producing data. So what does a short time series look like? On top, we have a well-behaved one, and this is like well over 3.5 years of data, which you'll see later is enough to generate a good estimate. But below, we have very inconsistent data. If you were subject to if you had in your system a GPS time series with this much data, you would not be able to get an estimate from it. We'll see why later that's too short for using the traditional methods. The traditional method is the least squares regression, which a lot of people which means it relies on assumptions with distributions like the normal distribution. It also takes into account the distance of every data point from the proposed slope. So every data point plays a role in this estimate. And as you can see, there's also a seasonal consideration for the least squares regression, and we'll see why. Van Dam et al. Actually was the one who proved that GPS time series are subject to certain seasonal variations. Snow can, as we know, the lithosphere expands and contracts, and snowpack and water can either expand it or contract it, and since the GPS time series are so sensitive, you can easily see that in the fractions of millimeters. And this is an example time series. It actually has a very high seasonal variation. It's synthetic, so not anything we've actually seen. But you can see those sine curves right there, and that's the variation that occurs with snowpack and groundwater. Fluid and Lavallee really inspired our project because they put constraints on how well certain estimators work. Above 4.5 years of data, you can use the least squares estimator confidently. Between 2.5 and 4.5 years of data, you're going to need to use the least squares estimator with a seasonal consideration, which has a sine term, so you can capture that movement. And below 2.5 years of data is deemed, there are no currently viable ways to estimate a slope from that short of a time series. And this is one of the conclusions of Fluid and Lavallee, and you can see that as the time span on the x-axis gets shorter, the velocity bias, which is how far the estimate is from the true velocity, blows up. And these biases are way too high for certain estimators. Our approach was called the Theil-Sen method. It's a non-parametric approach, so it does not rely on certain things like the normal distribution in its approach. Look here, the black line is the true velocity of this data set. The blue points are the data set. And the green line is the Theil-Sen estimator. You can see that it's very close to the black line, and it works very well. The red line is the least squares estimate, and that's actually not very close to the true black line, and it's affected by these outliers right here. I'm not going to get into the mathematics of it right now, but the Theil-Sen estimator has it's not affected by those outliers. And it was developed by Henry Telf, who's a Dutch econometrician, and Pranav Sen, who is currently a statistics professor at UNC. The seasonal Theil-Sen method, it takes into account the seasonal variation you see. Each of these sine curves represents 1 year. So when we choose a point, the Theil-Sen method relies on slopes within the data. So you have to choose a point, and the best possible slope you can get with that point is matching it with one that happened a year later. So that point was subject to similar environmental conditions as the first point. So using that slope is actually a very good estimate of the overall slope we see here. But since it's not exact, we want to introduce a DT, which is a little wiggle room. We'll see that that point right here was subject to similar environmental factors as points within this little range right here. So we don't want to limit ourselves to that one point. But we'll see later what qualifies how big DT should be. That's the wiggle room. Matching slopes between points that occurred at different points in the year is actually very bad for the Theil-Sen method. If you want to know some more specifics about how it works, come see my poster tomorrow. But for reasons that these 2 points were subject to different environmental conditions, you can see that this is not indicative of the overall trend. Points that are from similar times of year are much better. So we used a Monte Carlo experiment, which basically relies on repetitions of the experiment in order to learn something about what we have. This is a synthetic time series. On the y-axis, we have position, and on the x-axis, we have time of year. And we generated 250 of these for certain combinations of certain factors. You can also come to my poster to learn exactly what those factors were. We won't overwhelm you now. So for each of those groups of 250, we calculated an estimate using seasonal least squares, non-seasonal least squares, and Theil-Sen. So we want to see how well each estimator works against each other. And we're giving it 250 tries to get it right. So after averaging the estimates for each estimator, we wanted to see how far it was from the true velocity. We input a true velocity to each of these time series so we know how well each one performed. We want to give Theil-Sen the best possible chance against the least squares, which is so popular. So we wanted to see which DT was best. As we were discussing before, that DT is the wiggle room. We want to see how close we want to match points that were from similar times of year. And intuitively, you might say smaller DTs are better because that hones in on that one point that is most similar to that other point. So focus on these blue lines. As DT gets bigger, you have 0 days to 30 days, which is a month. We vary it from comparing those 2 points to points a month apart or even 0 months apart or days apart. We'll get into the theory's on my poster, so if you're really curious about Theil-Sen, we'll get into that. But basically what we see from this are smaller DTs are better. Honing in on that one point is much better for the Theil-Sen estimator rather than expanding it a month in either direction, which will be subject to the high seasonal signal. So this is the meat and potatoes of our conclusion. Was the Theil-Sen better or worse than each of these least squares? We confirmed the Blewett and Lavallee conclusion that the non-seasonal least squares, which is the least squares that doesn't account for that nice sign we usually see in GPS data, it did not perform very well at short time lengths. Right here we have time series of length 1 year, and we can see that it's already erratically becoming biased to the true velocity we see. And we were ultimately comparing Theil-Sen to the seasonal least squares, which was previously the best estimator we had. And we can see that it's definitely not an improvement, unfortunately. We had hoped it would be so we could capture the slopes of those short time series, but it definitely wasn't. You can see as time length increases, we have it honing in on that velocity very well. And when time series are short, it strays from the true velocity. So it was not an improvement, unfortunately. So why didn't it work well? We're not exactly sure, but what we do know is that we did not vary all the possible parameters that occur in GPS time series. We have things like white noise and seasonal signal, which we accounted for, but there are other things like flicker noise that are very common in GPS data that we did not simulate. So since this is a foundational study, if someone chooses to continue, or if we choose to continue, we will consider factors like flicker noise, other types of phenomena that occur within GPS time series. And Jeff Blewett, who's a member of the department at UNR, who's very familiar with the types of data, we were discussing it with him a bit, and he decided to apply the Theil-Sen estimator to these types of time series, which have a step, and you can barely see that dotted line right there, but there's a step right there. You can see that here the velocity is about 0, and also here the velocity is about 0. But something happened in the middle. Could have been an earthquake, could have been a change in instrumentation, but we don't know. What Jeff's doing is he's using the Theil-Sen estimator to find this overall consistent velocity while factoring out that step. And he's actually having very good results. And we could also talk about that more if you do stop by my poster tomorrow. And I would like to thank all these amazing people for helping me throughout the summer. Not that you can see the top. Corné is my mentor. Brett and Bill took me out in the field for many days, and we drove many miles. This is the Grand Canyon, and this was just awesome. And Jeff Blewett, who was amazing in helping us with the estimator, and Young and Sherry were also in the department. And again, thank you to UNAVCO and RESESS, and you're all awesome. Any questions or comments? Hi, Christine.
All right, any questions? Oh, just a quick note to folks who are joining us via WebEx. If you could please turn off your cameras, make sure you're not doing video conferencing, or at least turn off your camera so we're not doing anything. Thank you.
Christine and then Glenn.
All right, so you were using entirely synthetic time series. Okay, so were you using entirely synthetic time series for this?
I could tell you would catch on to that, Christine. We did apply the Theil-Sen Estimator to actual data. It didn't produce very conclusive results. It didn't perform very well either, but that's also on my poster, so we could discuss that. But yes, we were using synthetic time series to capture it because we do know those true velocities in there.
Yeah, that's probably a good plan. Were you, when you're generating a synthetic time series, did you take into account climate, like drought, for example?
We did not. Our synthetic time series were solely based on the parameters we input, like seasonal signal. It wasn't directly reflecting any specific site we had in mind.
All right, thanks.
Thank you for the question. I'll talk quickly. No.
All right, thanks, Glenn. I'm sure you can see him at his poster. All right, thank you, Brian.
No problem.